Hey guys, all right, let's listen to Professor Dave talk about kinematics part one. So the rest of the lectures for this week will be going over chapter one of your book. And yeah, all right, let's get to it.
Hey, it's Professor Dave. Let's talk about horizontal motion.
He knows a lot about the science stuff. Professor Dave explains.
As we learn classical physics, a big topic of study will be mechanics. This is a branch of physics that can be divided into two smaller topics, kinematics and dynamics. Kinematics, which was developed largely by Galileo in the early 1600s, deals with equations that describe the motion of objects, without reference to forces of any kind, whereas dynamics is the study of the effect that forces have on the motion of objects. These topics together comprise mechanics. We are going to focus on kinematics over the next few tutorials so that we can familiarize ourselves with the ways that simple equations will govern the motion of objects in 1 and 2 dimensions. These equations are revolutionary because from Aristotle until Galileo, we thought that mathematics could only describe the perfect motion of divine celestial objects, and that the motion of objects on Earth was too imperfect and unpredictable to calculate. But we soon found that the same equations govern the motion of all objects, whether on Earth or in space. It is simply that on Earth we must make approximations, since there are a greater number of variables, like friction and atmosphere, that affect motion in various ways. The kinematic equations include variables for displacement, velocity, acceleration, and time. And in the context of kinematics, acceleration will always have a constant value, whether positive, negative, or zero, since we won't look at forces that could cause acceleration to change over time. When you see a subscript of 0 after velocity or displacement, it indicates initial conditions, which will have some implication depending on the problem we are looking at. Here are the 3 fundamental kinematic equations we will be using. The first one says that the velocity of an object at any time t is equal to the initial velocity plus the acceleration times time. The next one says that the position of an object with respect to a point of origin will be equal to its initial position plus the initial velocity times time, plus 1/2 the acceleration times time squared. Lastly, this one says that velocity squared is equal to the initial velocity squared plus twice the acceleration times the displacement. Other supplemental equations include these two, which are easily derived from simple definitions, which state that position is equal to the average velocity times the time interval, and that the average velocity is equal to final velocity plus initial velocity over 2, which is the definition for any average. Now that we have these equations and know what all the variables mean, we are ready to apply them to real examples of motion. Say you get in your car to drive to the supermarket. While at rest, you place your foot on the gas and apply a constant acceleration of 2.5 meters per second squared. What will your velocity be after 10 seconds, and how far will you have traveled in that time? We can use these two equations to find the answers. We just have to plug in what we know. For the velocity, we know that the initial velocity was 0 because we were at rest. So we just multiply acceleration by time and we get 25 meters per second. That is the velocity of the car after 10 seconds. Now to find how far you will have traveled, you will use this equation. Once again, initial velocity is 0, so this entire term can be ignored. Then we have 1/2 times the acceleration times 10 seconds squared, and we should get 125 meters traveled over this time span. So it really is this simple. You just choose the equation that is appropriate for what you are solving for, and plug in what you know. Let's now consider a car that is already in motion with a velocity of 27 meters per second. Let's say you need to stop suddenly, so you press on the brakes, initiating a rapid deceleration of negative 8.4 meters per second squared. How long will it take the car to come to a stop, and how far will it travel while your foot is on the brake? Once again, let's use this equation to solve for time. It must be this equation because we know everything in it except for time. For velocity, let's plug in 0 because we are curious about the time elapsed at the moment that the car stops moving, and the velocity when it has stopped moving will be 0. The initial velocity is the 27 meters per second we mentioned, and we can plug in the acceleration, solve for time, and get 3.2 seconds. Now that we know the time associated with this event, we can use this other equation to find the braking distance. We plug in the initial velocity and acceleration we mentioned before, as well as the 3.2 seconds we just calculated, and solve for x, which will be about 43 meters traveled from the moment you applied the brakes to the moment that the car stops moving. These equations work for any other object just as they do for cars. So let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, Professor Dave Explains.
All right. That is Professor Dave on horizontal motion doing a fantastic job breaking it down.
at gmail.com.
So very quickly, just this is just a recap of what I was going over with displacement. So the origin and the final position is the displacement, and remember, displacement is not total distance traveled. So velocity here as a vector is the displacement over time traveled, okay? Again, velocity doesn't take into account the total distance. It takes into account the displacement. Now you can start to look at the smaller amounts of displacement versus smaller amounts of time to get a more accurate velocity, and we may delve into that later. Acceleration, just like velocity is the change in displacement over time, acceleration is the change in velocity over time. Here's some good examples. This is also from the book. Oh, okay. So we have acceleration can be constant, and with constant acceleration, there's a constant change in your velocity. So velocity is 0, acceleration is 2 meters per second squared. Then after 1 second from being 0, your velocity is now 2. And 2 seconds later, it's now 4. 2 more seconds later, it's then going to be 6, because 2 times now a total of 3 is 6. Then at the 4-second mark, 2 times 4, 8, so on and so forth. So if we're looking at, and this is with the initial velocity being 0. So we see right here, acceleration, change in velocity over change in time. This can then say written as, actually here, let me write this out. This can then be written as change this delta, that's what that triangle is called. Delta V is the same thing as saying final velocity minus initial velocity. Okay. So then this is then A equals that delta V. I'm going to put this like this. V final minus V initial over change in time. So say just time in general, okay? Then we can then look at this and shuffle this around. Let's move this guy over here. All right. And let me sort of clear this up a little bit. Good. This right here then becomes T times A equals V, oh, the VF minus VI, okay? Now, if we want to just get the final velocity, then we're going to move this over here by adding it to both sides, okay? So that's going to give us so we're going to add that initial velocity to the other side. So then we get V I plus that. And then we see here, that's how this equation comes about. Now, if the initial velocity, this is 0, well, then that's just 0, which is where we get this. So, and this is kind of easy to look at. So let's do some dimensional analysis on this, just to get an idea of how this works and how you can check your answers. So what is velocity measured in? Okay, velocity, let's say, is meters per second. So it will say meters per second, okay? And it could be 5 or 10 or whatever. That doesn't really matter. And I'll just say let's just say x meters per second. X meters per second equals some, say, y, we have acceleration, y acceleration, and acceleration is meters per second squared. And then we're going to say that's multiplied by some unit of time. So we'll say z. Oh no, that z looks too familiar to other things. Say, say equals c. Yeah, let's go with c. Seconds. Oh, seconds. Let's move this seconds over here. Okay, c seconds. All right. So v equals at. So x meters per second equals y meters per second squared times c seconds. Let's actually get rid of this. Let's get rid of the actual values and just stick with this. See how we can check our answers. Okay. and see how this makes sense. Okay. If we look at this specifically, just this section, I'm gonna draw this right here, down here. So this is meters over second squared times s, and s is the same thing as saying s over 1. And we can then see pretty clearly that these can cancel out, right? And then, well, when that cancels out, then we're just left with equals meters per second, which is the units of velocity. So you can always use, and this is called dimensional analysis. You can always use dimensional analysis to check your answers, make sure they make sense. Ooh, get that all of that still stays right there. Let me get rid of all of this. Okay, so equations of 1D motion. This, well, R is being as displacement. This is just the change in R. Of course, that's going to, so the final initial is sometimes written as 1 and 0. You're going to see this in both ways. You're going to need to be able to recognize it in both ways. So R1 is R final, R0 is R initial. That gets confusing because the 1 can be misinterpreted as an I pretty easily. So you'll just have to just be on the lookout for that, and it will pop up further on just through the book and other readings. Velocity, again, velocity is change in position over change in time. Change in position over change in time, and acceleration is change in velocity over change in time. All right, and then when t equals 0 and a is constant, that helps to simplify it, or t initial t or t naught. That 0 is it's pronounced as t naught. This is v naught, and then you'll see a naught, and so on and so forth. And that helps to simplify the equations a little bit. All right, so now let's get into kinematics part 2.
Professor Dave here. Let's discuss vertical motion.
He knows a lot about the science stuff. Professor Dave explains.
We have familiarized ourselves with position, velocity, and acceleration, as well as the kinematic equations that govern the relationship between these parameters. We also saw how we can apply these to simple horizontal motion, and things will be essentially the same when looking at vertical motion. The only difference is that when examining strictly vertical motion, the acceleration will be the acceleration due to Earth's gravity, which is a constant, negative 9.8 meters per second squared. This value is unique to the Earth since the Earth has a particular mass and radius. This value would be different if we were on some other moon or planet. But we humans tend to spend most of our time here on Earth, so we can just associate acceleration due to gravity with this value unless otherwise specified. Also, with horizontal motion, it is arbitrary which direction we regard as positive or negative, though we often assign the positive direction to the right by convention. But with vertical motion, the negative direction will always be down towards Earth, and objects will always accelerate towards the Earth, since that is the main source of gravity we experience every day. We can examine objects that are in free fall, which means they were dropped downwards from a standstill, or we can look at objects that have some initial upward velocity. Either way, acceleration will always be negative 9.8 meters per second squared when on Earth. Let's say, for example, you drop a rock off a 100-meter tall cliff. How long will it take to hit the ground, and how fast will it be traveling when it lands? To answer this, we will need the equation regarding position, because we know that the rock must travel 100 meters in the negative direction. We can plug in negative 100 here. For the initial velocity, that will be 0, because when you drop the rock, it is from a complete standstill. Only once you let go does gravity cause the rock to accelerate towards the ground. So this whole term can be ignored. Now we plug in the acceleration due to gravity and solve for t. Notice that the negative signs on position and acceleration values will cancel out to give a positive value for time. This is very important, as we have to be careful with signs as we do arithmetic, and this will be a common opportunity for error with many students. And we get around 4.5 seconds for the time elapsed during freefall. Now if we want to know how fast it is going when it hits the ground, we can use this equation to solve for velocity. Again, initial velocity is 0, and we have negative 9.8 meters per second times 4.5 seconds, which gives us negative 44.1 meters per second at the time of impact. This value is negative because velocity is a vector, and the object is traveling in the negative direction. Now let's say that we take another rock, and this time we throw the rock straight up in the air with an initial velocity of 10 meters per second. This velocity will immediately begin to decrease because of the negative acceleration due to Earth's gravity. The moment it leaves your hand, the velocity will decrease until it becomes 0, and then grows in the negative direction. This means it will travel upwards for some amount of time before falling back down to the bottom where the other rock landed. How long will this rock be traveling before it lands? Well, let's do the same calculation that we did before. The only difference here is that instead of an initial velocity of 0, we have an initial velocity of 10 meters per second in the positive direction, or upwards, and the usual acceleration, which again will be downwards and therefore negative. We plug in negative 100 meters for the displacement, remembering that even though the distance this rock will travel is greater than the other one, both rocks start and end in the same place. Then we plug in the other numbers. What we are left with is a little trickier than before, because we have both a t and t squared term. This means that we will have to use the quadratic equation. If you have forgotten this from algebra class, here it is, as it applies to an equation in ax squared plus bx plus c form. We simply take the coefficients of the equation and plug them into this expression, and we will get two answers as possible values for x. So we have to take our equation and rearrange it to look like the standard form, which involves adding 100 to both sides. There's our a, b, and c. If we plug those in, we get the two values for x, but the positive answer is the one we are looking for, as it doesn't make sense to discuss negative quantities of time. So we can conclude that it takes 5.65 seconds for this rock to hit the ground, a little over a second longer than the one we simply dropped. How fast will this one be traveling at the point of impact? Let's use this equation again. This time we have to use 10 meters per second as the initial velocity, and then we plug in our acceleration and the time we just calculated. This will give us negative 45.4 meters per second at the time of impact, a little more than the other rock because it fell from a slightly higher position, the peak of its trajectory. So we can see that motion in the vertical direction utilizes the same equations and concepts as horizontal motion, except that the acceleration will always be due to gravity, which is held constant at this value. Let's check comprehension. So I can keep making content. And as
All right, guys, that is part 2 of kinematics.
always, feel free to email.
And next we will be delving into projectile motion, and then I have another simulation that hopefully you guys find enjoyable. let me know. Send me messages on some of these, and I'll see if I can find better resources if you find them useful or not. All right, let me stop recording.